I really just, to begin with, I want to know, explain to me what you do. You've kind of given me a background for it before. It's been a while. So
Mhm.
I still remember you work with lasers. I know you've been working with cardiovascular mapping or something with
Yeah.
lasers. I remember that. And I remember how expensive your lasers were and how expensive your detectors were. But that's it. So tell me what it is, what's your title and what you're actually doing.
Yeah, so right now I am an assistant professor in medical biophysics and biomedical engineering here at Western. So I started my faculty position in 2013 actually as a Lawson scientist. So Lawson is a research institute here in London, and it's the research institute for all the hospitals in our city. So London is about, I don't know if you know our location. London, Ontario is about 2 hours from Detroit, 2 hours from
Okay.
Toronto, and about 2 hours also uh, from Buffalo.
Okay.
So we
So
are
right in the middle of that triangle.
exactly right in the middle
Okay.
of that triangle. So it's very well positioned. So we are not far away from any of these large cities. So London and surround London is about 400,000 people, and we serve a population of about 1 million people.
Okay.
When I say we, this I mean that the hospitals in London.
So that's got to be, I mean, y'all are so close to it. I would imagine the predominant clientele or patients that you service are Canadian and not American,
No, they are Canadian.
all
They are all
Canadian. But
Canadian. We are very close to the border. We are
okay.
about an hour from the border, but these are all Canadian people and mostly a rural area. So we don't reach to Toronto, even not to Waterloo. So
Okay.
we are a major center, like cities that are at the border in of the United States, like Windsor.
Okay.
They have serious cases. The likelihood is that they will come here, and also there is another city called Sarnia that is at the U.S. border, about an hour from here. If they have serious cases, they will bring it to London.
Okay. And so, I mean, you guys, I think what, about 2 hours from Toronto, right? South?
Yes,
Okay. So you're servicing, I would imagine, from halfway to Toronto and down, because I'm sure Toronto has its own kind of
yeah,
radius as
yeah,
well, right?
yeah. So Toronto has its own radius, and even for some cases from us, like we don't do neonatal cardiac surgery.
Okay.
If there is a neonatal cardiac surgery in London, they would be going to Toronto.
Okay.
So
And
there are those very specific specialties, and there are very few, but there are some of them we don't do here.
okay. And seeing that you don't do those, do you guys have a specialty? Because you guys have the imaging center, which
Yeah, no,
seems
we are
large.
extremely big for imaging.
Okay.
Yeah,
We
no, this city does almost everything. But in Toronto they have Sick Kid,
okay.
which is equivalent to Boston Children or
Okay.
Children's Hospital of Philadelphia. So and Sick Kid plays in that league. It's one of the top children's hospital in the world. So,
Okay.
but they are in Toronto. So we have here a neonatal intensive care unit that we work with. They have a lot of, yeah, they're very, very good. But
Okay.
we don't do neonatal cardiac surgery. That for sure I know because that's one of the things that I'm interested in.
Okay. And
So yes, going back to who I am. So an institute scientist. So I'm a research scientist at Lawson. So I have a lab there, which is in the hospital. So Lawson is the research institute for all the hospitals in London, which include St. Joseph Hospital and Parkwood Hospital. We also have LHSC, which is London Health Science Center, which includes University Hospital and Victoria Hospital. Victoria Hospital is where the Children's Hospital here in London is located.
okay. And you have
So
two two locations, right? Is that
yes,
still and it was St. Joseph?
yeah, St. Joseph Hospital,
Okay.
which is yeah, part of Lawson. That's one of the Lawson lab. So here in London, anytime you see research done in a hospital, it's done by Lawson scientists.
Okay. How many Lawson scientists are there?
Oh, a lot. So just our imaging group is about maybe I would say maybe 20 people. or more,
Okay.
20 PIs in the imaging group.
And is that mostly physicists or engineers, or is that also beyond
Yeah,
that?
it's very diverse actually. We have colleagues who are radiochemists.
Okay.
They make radiochemical compounds that are used in human because we have a cyclotron in the
I re-
basement of the hospital.
I remember this. Yes. Okay.
Yes. We have cyclotron in the basement of the hospital, and they make radioligand that are used in human, and they ship it out as well for us to other hospital around here. They have a business plan, they sell, and they are very very good.
Okay.
And we also have I have colleagues who are biologists, and they work with biological cells to label them so that we can image them.
Okay.
Because we are the imager, we make the
Yeah.
images, but
Yeah.
we should be able to image something. So these chemists make things that we can image in the body. So
Yeah.
this radioligand will come into the body and attach to specific organs so that we have better contrast. So
Okay.
we have other colleagues who are biologists, and they work on those aspects. So yes, very diverse, but
Is
mostly physicists. So the
okay.
largest part of the group are physicists.
Okay. Um, as for the radioactive particles, do you have a typical one that you usually work with? You yourself work with
So
when the chemist brings it?
no, because I'm a physicist. So in physics, those radioligands are used for positron emission tomography (PET),
Hmm.
because some of my colleagues are expert in PET imaging. I have colleagues who are expert in MRI imaging,
Okay.
many type of MRI imaging. We have a PET MRI, which is a dual machine that can do both PET and MRI in a single machine. We have the very first one that has been ever installed in Canada. So it's
Do you have any idea how much that costs?
uh,
And
yeah, a few $millions.
okay.
Yeah, we have also a PET
And
MRI, which
okay.
is a dual PET and MRI, a PET CT as well. Sorry, a PET and a
Okay.
dual PET and CT, a machine that does PET and CT in the same machine. These are very important because sometimes you want to do both imaging, and in most centers, the people will be imaging one and imaging the other, and image registration, co-localization is a huge issue. So we can do research or imaging that cannot be done in many places or
And
elsewhere.
CT connection, that's simply because PET has very bad spatial resolution, right? So the CT aligns it with its actual
Yeah. So the
position.
PET, yeah. So PET is extremely sensitive. It is a functional imaging technology, but it has poor resolution, like optics. There is a very
which
good
is which is what we'll
very
get
similar.
into.
That's very good similarity there. They are very sensitive. They are functional imaging modalities, but they have low spatial resolution.
Okay.
In contrast, CT has very high spatial resolution, and also MRI as well. So that's why they are combined with MRI and CT, so that they can use the anatomical information that you get from the CT and you overlay on top the PET images and makes beautiful images.
Okay.
Not just beautiful, but diagnostically and for research, for science, for a lot of things. We also have a Revolution CT, which is an extremely fast CT
Okay.
image from G, and that's one of my colleagues. He was one of my mentor, Dr. Tingley, and they use it for CT perfusion. He's one of the world, if not the world expert in CT perfusion.
Okay.
He's measuring.
I've never seen or heard of CT perfusion.
Yeah, CT perfusion is a unique technology because you inject a contrast agent, which is an iodine-based contrast agent, and that causes attenuation of X-rays, and that allows you to measure, by measuring this attenuation and doing correction, you can measure, and applying some algorithm, you can measure the perfusion to the brain, to
Oh
many organs.
wow.
They do cardiac,
So
they do.
so that's almost, I mean, that's in a way kind of like a functional MRI.
It is a functional. It's called functional CT.
Yeah.
It's the functional.
Okay.
Yeah, it's a functional imaging modality. They do cardiac.
I've
They
never
do
seen
now.
this before.
Yeah, they do renal imaging. No, we are a small city, but huge in imaging. And I'm
Okay.
just talking. I have been just talking about just a few applications that are done by my colleagues uh, at Lawson. I'm not yet at the university because my main appointment. So about 3 years ago, I was officially recruited by the university because here, when you are an institute scientist, you have an affiliation of the university.
Hmm.
But now my paymaster is the university, so I have been moved to the university. So I still maintain a lab at Lawson, at the hospital, St. Joe's.
Okay.
But I have my main lab now is on campus at Western University on the
Okay.
campus, and I'm part of the medical biophysics. I'm one of the core department
And
researchers there.
I
That's
think
where my lab is now.
I think when I visited, you had just made the move.
Yes.
Okay, so now I'm betting it because your lab was just like you had just gotten your table in.
Yeah.
You had gotten, I think, a bit of equipment, but it wasn't completed.
No. No.
So how's it looking now?
Yes. So I am still very careful because I need to buy a very expensive laser.
Well, I remember,
And
I think the one you showed me, it was the big black box that had a single laser and I think a single photodiode, but it was huge. And I want to
yeah,
say that you said if it were to sell, it would be about $1 million.
uh,
Was
no,
that? I mean, I don't think it
oh,
was commercially
okay,
available.
I see. But that one has a lot of laser inside actually, and a lot of
Oh,
detectors. And it
okay,
was
okay.
a hybrid system. You see it like as a box, but it was a complete optical system. It was actually very advanced. I
I
would
I
say
I recall
one
that.
of the most advanced optical system you will get in this on the market.
Okay,
If not the most.
okay. I
Yeah,
remember
yeah.
being in awe
That
by
one
it
would be expensive
because I think
because
the
it.
laser was that big.
No, there were a lot of laser inside that
Okay,
system. So there
okay,
were diode lasers. Those diode lasers are not too expensive. I would say maybe around 10 to 15 thousand
okay,
each. So we had three lasers there, and we have four detectors, but we have a DCS laser there
okay.
plus I think 8 or 16 detectors. So yeah, that's what made that system quite expensive.
Pricey. Okay.
Yeah. So if you were to design it, build it, and sell it, then that will be that will be close to $1 million probably
Okay.
to sell it.
So, um, okay. So let me ask then. Working with your lasers, having your lab set up now. Of course, waiting on this new piece of equipment. What current research are you working on? Last I
Yeah,
heard,
so
you
I have the
had.
other equipments. So we're still going, and I was able to get one of the company that sells this laser to lend me one of their laser, and we did a demo, and we're pretty happy with that laser. So the likelihood is that we will go with that laser and buy it. That laser is about 120 with some option. We can go to 150.
Okay.
So we have put money aside for that. We're trying to apply for funding and see if we can um, fund that laser from those funding. But if not, we'll just use that money that we put aside to buy that laser because it's a critical piece of equipment for someone who does optics.
Yeah.
Because it's a bright light source, you can use it for many applications.
Okay. And
So that laser would not be a laser that you would be using like in the bedside in the clinic. The goal is to get it to get that laser as a light source in the lab, and then it will help us define what kind of wavelength we want, what kind of power we want. You know,
okay.
once we get all of those things parameterized, then we can go out and seek cheaper lasers that will do just specifically that. But this
Yeah.
laser is a broadband, high power, time resolve pulsate laser, so per second laser.
And the time
This
resolve
lab.
the time resolve laser, that I mean that's literally you're sending when you send a pulse of laser, how many photons are you sending? Is it one? Is
Well, you
it
send a lot of photon. You know, pulse of laser, you have millions of photons. But what you do is because in our case we look at turbine media, tissue, biological tissue, living tissue is a turbine media. As a physicist, I see it as a turbine media, which is a medium that scatter light a lot, so that if you had a chance to look at the photon, they will look like a cloud moving through the tissue.
That's a fairly fascinating thought right there.
Yeah, it is.
Okay, okay. You have me
so it
smiling.
looks like a cloud of photon moving through the tissue. So what we do, and because of that, so you have a lot of attenuation. So where you put your detector, you make sure that you attenuate your light source so that you're detecting one photon for every 100 pulse.
Okay.
So every time the laser pulse, 10 times, 100 times, you have a probability of detecting one photon.
And how, I mean, if you were to throw a number on it, every pulse contains how many photons?
I would say millions of photons.
Millions. So you're getting, so 100 million photons coming in, you're getting one photon out.
No, not just one photon. Yeah, let's say exactly.
You measure one.
Millions.
Okay.
Yeah, so if you consider that, I have 1 million photon in one pulse, so yeah, every 100 million, you're only detecting one.
Oh wow.
But these lasers are so fast; they emit in the megahertz. So you have a laser pulse, laser train, the whole train. Every laser will emit a pulse every 12.5 microsecond.
Okay.
So in 1 second you have millions of photons.
Yeah.
So, and that's why we can and what we do is we have this very sensitive detector. They are photon counting detector. They can count a single photon. And what we do, we use this technology called signal photon counting, where when you receive a photon, you measure the time and you say, okay, well, I have one count. It doesn't matter what's the amplitude or the pulse of the laser. So you just make a count. And then you build a histogram.
Okay.
You build a histogram. So every time I have a count, I increment the time. So the time, time is my x-axis. Every time I have a photon, I increment, I put one count in the time bin. And I do that. And over time, what's happened is that because you're doing a statistical sampling of your pulse, you can reconstruct your pulse, the entire pulse of light.
Oh, wow.
Yeah.
Okay.
Just by using that. So it's nice because you're no longer limited by some of the characteristics like the pulse response of your detector. So you can have very narrow, you can measure very narrow pulses with a detector that doesn't have like those very fine temporal resolution.
So with this, what are you applying it on right now? The last thing I remember was the hand grid.
Yeah, so that is one of the applications that we have, because one of the applications we want to do, so we're still working on it, is to develop an advanced imaging technique that will allow us to make images of hands. So why do we choose hands? Because we are interested in rheumatoid arthritis. And rheumatoid arthritis most of the time will affect the hand joints. Mm-hmm. And because optics is very functional, it's like a pet, but much cheaper and safer, because in optics we use light.
Yeah, and you don't need a cyclotron downstairs for it, even though you have one.
You don't need a cyclotron. It's mobile. It's safe. You're just using light. And it doesn't expose the patient to any radiation or the operator. It's much cheaper, and it's much more versatile than PET actually, because you have a lot of endogenous chromophore in tissues that you can measure. For example, you can measure hemoglobin, all this.
Yeah.
Water and all of that, and you can also inject indocyanine green, which will go to the joint. And people have used similar approach, but there was this planar imaging where they have a CCD camera that looks down to the hand and take an image.
Okay.
Which is good. It's not bad, but it doesn't provide you a 3D image.
So that's like, it would basically be a comparison of an X-ray.
Yes, exactly.
Okay.
It's similar. What you'll get there is the equivalent of an X-ray. And what we want to do is to do the CT, the CT equivalent.
Yeah, okay.
Do the tomography, so that you can take the image and rotate it and see where where these where your probes are within the hand,
So
or
explain.
where your contrast is within the hand.
So explain to me then, how does this, so I mean I'm picturing it, and I can kind of understand how the light would differentiate in some ways between tissues. But when you're looking at rheumatoid arthritis, what are you looking for?
Yeah, so rheumatoid arthritis is known to when you have inflammation in joints, because that's a hallmark of rheumatoid arthritis. It increases the concentration, it increases inflammation in the joint, and because the joints are inflamed, so you have inflammatory cells that moves into the joint and start to fight the inflammation. And because of that, so you have a very thin layer of tissue in the joint. It's called the synovial membrane. So the synovial membrane start to become inflated and start to increase in size. In normal people who don't have any inflammation in their hand, the synovial membrane is about a few tissue layers. But
Okay.
if you have rheumatoid arthritis, it increases to more than 10 layers. So
Okay.
this is an increased size, and increase in cell mass require increased flow, increase metabolism increases, and because of that you have and you also have angiogenesis, which is a formation of new blood vessels in the region to feed the increased cell mass, and all
Okay.
of that make that region so the blood volume, which is the volume of blood in that region increases, and also the blood flow in that region increases, and also oxygen saturation in the region changes, because that region, although you have higher flow and higher blood volume, the region is ischemic, and has been shown using invasive probe.
So
People have shown that arthritic or rheumatoid arthritis joints are hypoxic, so that you're going to have lower saturation in the
so
joint.
it's just
These are all parameters that we can measure with optics.
okay, so it's just like sitting blood or sitting fluid in that area. It's not moving
Yes.
through as it should.
Well, it
And
moves. It moves, but the quantity, like you can see it as a pipe. So the pipe you have more pipes, and then if you look at the entire number of pipes, and this pipe they hold more liquid.
yeah.
So more blood. You have increased blood in that region, but yeah, you have also increased flow, and you also have less oxygen saturation in that region. Going to be
Okay.
lower because you have a hypoxic region.
So I never knew that arthritis developed more blood vessels. I didn't, I knew that quality of tumors.
Yeah, actually, the arthritic joint has a lot of similarity with tumor, a lot of similarity.
I mean, that sounds interesting to me.
Yeah,
Is
that's
that
why
an
people
area?
actually, yeah, one of the best therapy for rheumatoid arthritis, these are TNF blockers that are used also in cancer.
Interesting. Okay. I did not know this.
Well, this is a physicist learning biology.
This is great. Okay, so you have this project going on. Do you have any other applications that you're working on? So you have rheumatoid arthritis. Is there anything else that's in the arena? And if there's anything that you can't talk about right now, just feel free to skirt anything.
Yeah, so uh, during my training, I did a lot of brain work on brain, and we have
Okay.
done quite
I, I
significant.
have to interject. As a physicist coming into the brain,
Mhm.
how it was there anything that you noticed that was just different in your view of it? Because I came from exercise science and I got into engineering,
Yeah,
and so my view of the brain changed a lot when I got into engineering because you start speaking in terms of like control centers and wires, and interconnectivity like you would telephone poles. Whereas in kinesiology and exercise science, you don't talk like that. And it was a very
yeah,
enlightening way. And you came kind of the other direction. So was that
yeah.
do you think that was favorable when you see your colleagues who did not come from that direction? You know, when they start from biology or physiology or whatever it might be?
Yeah, so for me, I was lucky that I came to a lab where my to do my postdoc because I started working in biomedical optics during my second postdoc. And that is actually an interesting side of things that we will be talk about because so I was trained as a physicist. I did my undergrad in physics
Okay.
in
And
Senegal, in
okay, I was gonna say where
University
in,
Cheikh Anta Diop,
okay.
yeah, in Dakar. So, and when I graduated in 1997, I went to Teachers College while I was doing my master's.
Where were you doing your
So
master's?
yeah, so I was trained as a teacher, and I was actually positioned during the school year in a school where I had to teach physics and chemistry to high school student
Okay,
for a
still in
term.
Senegal, right?
Still in Senegal, and
Okay.
that school was Lycée Lamine Gueye, and this is in the center of Dakar.
Okay.
And so I teach there for one term. And so normally I was supposed to have my mentor in the class anytime I teach. But after a few, lessons, the guy just left, and I was left
Was that
in the students.
was that because he thought you were very good at it, or was he just very
I think
lazy?
I think I got a good handle of the class. I was young at the time, and
But
you know,
you're not a small guy. You're
and at
you're
the
fit. You're
time,
fairly,
yeah,
you have some stature to you.
yeah, I think the kid realized that this guy is no kidding. I wasn't kidding at all. I would come in, and I was extremely serious. Now I
Yeah.
am a little bit softer. I was very
You have
serious, very
you have kids now.
focused. Yeah, kids helps a lot. So I was very serious. I would prepare my lesson. I would come in class, and they would realize, and I would come in, and even when in this called cold period in Senegal, where it's going to be between 16 and 18 degrees Celsius. So that is
That's like here.
no, yeah. So that's
Yeah.
yeah, and that's maybe like I would say 60, no, maybe
I mean like
65
50.
Fahrenheit.
It might be 50. Hold
Yeah,
on.
Fahrenheit, and then I would, but I would be sweating because the guy is like really pumped, ready to go, and I will come in class, very well prepared, do my class, no joke, and if anybody is
So
trying to kick around, then I will handle it.
were you like that as a student? As like a high school, middle school student?
I think I was very serious in class. I wouldn't
Okay.
joke around with the teachers. I loved learning, so
Okay.
that when I got in class, I was very serious. I wouldn't. Any of my teacher will tell you, no, sometimes most
You
of
were
the
a good
time they
student.
wouldn't even notice me until we have assignment or anything, and they'll realize, oh, who's this guy? But most of the time, I will be like, yeah, the guy who doesn't speak, doesn't talk, very quiet.
And you got decent grades throughout that time?
Oh, I was pretty good.
Okay. I
Yes.
was I was okay.
I have always been like among the top in my class,
Okay.
like from primary school to university.
Okay.
It wasn't because I was smart, because I work hard. I work
Yeah.
really hard.
You knew what you
It's
wanted
all
to
that.
do. And I mean what I'll get back to it. I'll get back to it. So you're teaching this class. This is
Yeah. So
after your master's, right?
no, during my
During
masters. So I
masters.
was,
Okay, okay.
yes. So I was, and yeah, it was a lot of juggling. It was maybe one of the one of the busiest period of my life. I didn't have time for anything else. I was just going to teachers college, teaching this class, and doing my masters where I have to take classes. It was a very busy, very heavy schedule. Yeah, but roll my sleeve and handle it, and did very well. Actually, I graduated from my teachers college with the highest mark of my class.
Congrats.
So I was very, yeah, valedictorian of my teachers school class. So,
So how long did you teach after this? You have your
and
teaching
yeah, I had my
yeah,
teaching degree.
degree.
Normally, I was supposed to be recruited and become a high school teacher. But at the time in Senegal, there were, um, you know, was tough economic period because so I wasn't recruited. So I continued and finished my master's, which was for 2 years, and then stay there for an additional year as a PhD.
Okay.
Things were not moving in the direction that I like it. So I had a chance to interact with a Canadian scientist who came and visited our lab, and he offered me a position in his lab, and that's how I moved to Canada
And
to
was
do my
that to
PhD.
London?
No. It was in Quebec because
Quebec.
I
Okay.
speak French.
Oh, of course, of
Yeah.
course. It didn't even click. So,
Yeah, no.
but in Senegal, you also learned English, correct? It was French, English,
Well, I learned
and
I learned English until high school.
okay,
I would say pretty good compared to the class. To
but
overall
but
I was
better in
good.
French.
Well, no, my English was poor.
Oh,
If you compare to the standard of here, it was poor.
okay, okay.
Yeah, we don't speak. We read, and it was 2 hours
So
of English every week,
I would
basically.
imagine it compares to my Spanish then.
Yeah, probably.
Probably
But
the
your Spanish
Texas
maybe
the
your
Texas
Spanish may be
Spanish.
better than mine.
Well, I have a Puerto Rican wife, so I'm
Yes, I
picking it up
know.
fast.
That's why I think yours is probably much better than what my English was.
Okay. So so you got your PhD, you met a researcher from Canada. Did
No, I
you
had
come
my master's.
Oh, okay.
I had
Okay.
my master's and I was working toward my PhD. I was there for 1 year waiting for equipment. Didn't even really start for anything. And
Okay.
you know, that's one of the limitations that you have when you work in third world countries.
Yeah.
You have very talented people, people who are
Well,
really eager to work hard, but there are so many roadblocks that they
well,
face.
I remember when we first met in Mexico, there was a conference, and the conference was how do we resolve problems in Africa? And every answer was we need to make the education better. And I think you were the only African there. And you when we were talking, you said the education is fantastic. You said
Yeah,
it's better than anywhere else I've seen. The problem is there's no jobs. There's no
yeah, so people don't have a lot of opportunities, and education has degraded in many ways as well.
okay.
Because, and that's one of the things that I tell to my colleagues who stay back, who are university professor there
Yeah.
now. Anytime we have discussion, that we came back to that point. So you need education. Good education requires a lot of equipment, a lot of investment. And
Yeah.
these countries, they are under a lot of debt stress, so they cannot invest in education as they should be. And there is also some political issues
Yeah.
because a lot of these countries, they are not people have this choice between some bad guy, some terrible guy, and some okay guy. And even the okay guy will never be able to get in because there are political interference from mostly colonial power. In case of Senegal, it's France. France
Yeah.
has his hand and head in every corner of the politics in Senegal. And I want this to be in the court because I'm
You
really
want
pissed
it?
off.
We will keep it or we'll get
We will
rid of it.
keep this year.
Okay.
Yeah, so French has their hands and head in every single aspect of politics in Senegal, and they need to get out of Africa. Just let this country be.
Yeah.
And but they have way too many interests in there, and our generation and the generation after coming after us will fight it. We'll fight it to the
Well,
best of our ability
to
to get
be
them
fair
out of there.
though, to be fair though, y'all are giving France a terrific soccer team.
Yeah, you see,
Yeah. Oh man.
and that's only in soccer. That's only in soccer, and
Yeah.
it's everywhere. You go to France, you see, and you go to the research centers. Here we have international students from all over the world. I have international students in my lab. In France, you go, it's Africans.
Yeah.
The best students are from Africa, from the Maghreb and from sub-Saharan Africa. They are
Yeah.
the best students. They are eager to work hard. They are smart. They have the basic training. They come there, they roll their sleeves, and they work hard, and they become the best.
That's
So,
fantastic.
so
And
France really benefits from Africa, and that's why they don't want to leave African countries alone. But we will fight it.
yeah.
We'll fight to get them out there,
Yeah.
out of Africa. So we will continue to collaborate with them, do business with them, but we need to govern our own
You
country.
need your own.
Yeah, we
Yeah.
need to govern our own countries.
Yeah. That makes sense.
So yeah, after the political statement, so when
It
I
needs to
moved
be
to
said. It needs
yeah,
to be
when I
said.
moved to Laval, so I moved to Laval in Quebec City, where my supervisor was late Professor Roger Lessard, and he was a tremendous supervisor. I had the chance to have very good supervisor. My supervisor in Senegal, Professor Wanga, was also very good, very kind, and I still keep in touch with him. He's kind of like a father figure for me. So
That's
when I
terrific.
moved to Laval as well, I had a
I
chance to.
don't always hear that about supervisors.
Yeah, no, he's still a father figure for me. He was very kind, and I still, anytime I go to Senegal, I go and visit him.
What was this PhD in particular? So you left. So you got an undergraduate in physics. You got a teaching certificate, which I'm assuming, or teaching diploma, which I'm assuming was general, but you
Yeah,
were teaching physics and chemistry.
yeah.
And then you start working on a PhD. What was the PhD entitled?
It,
what was your
so I had a master's degree in optical spectroscopy
okay.
from Senegal. And then I moved to Laval and I started a PhD in optical materials with photonic crystals, still in physics.
Okay.
And so my PhD was on photonic crystals. And photonic crystal is high-tech materials that can control light in specific ways. So nothing to do with biomedical optics.
No,
And when I,
but
Mhm.
applicable. I
Yeah,
mean
yeah,
that's
no,
yeah.
yeah, yeah.
Yeah.
It is. Actually, one of the lasers that I want to buy is based on photonic crystals. It's based on photonic crystals fibers. So
so so I mean I'm assuming most of the stuff you study in that program, I mean, you're doing your research, but you probably had to get more adept at lenses and about refractions and things like that. What were the what was the curriculum like? What were you having to cover?
okay, so that's a great question actually, because Laval University is with Rochester's the two best university in North America to learn optics. So I
Okay.
was very lucky.
Yes, you were.
So to end
Well,
up
not
in
lucky,
Laval.
not lucky. You worked your butt off to get there, but
But that was a fluke because I didn't know that they were that good in
okay.
optics. So they have this center called the Center for Optics, Photonics, and Lasers. And if when you do your comprehensive exam at Laval, at my time, it was an exam, a 3-hour exam on anything optics.
Okay. Like
Yeah.
anything.
So
There wasn't
anything optics.
there wasn't oh dear.
No, yeah,
That sounds
yeah.
terrifying.
You have to know all the fundamentals of optics. And the book they recommended was the Hatch Optics. I don't know if you know
Hatch.
this. Hatch, yes.
I'm gonna write that down.
Oh,
I've been
I have
how
copies of them.
terrible is it?
No, it's a good book. It's an excellent book. It's a lot of things that you have to cover. You have to cover all the fundamentals of optics.
Okay.
So, but so at that time, this was a fail pass exam, and you have to pass this comprehensive exam in order for you to go through the program. So at the time, anyone who graduated who has a PhD from Laval would be excellent in optics. That was part of
Yeah.
and you have to take also, I think, 3 graduate or 4 graduate courses that was part of the curriculum. And then after that, it's doing
Research.
your research and publishing.
Okay. And then what was your research in that time period?
Yeah, so I arrived in Laval like almost was an interesting one because I arrived around I think it was November 12 to November 13 in
Okay.
2000.
Oh God. So you went from Senegal to Quebec in the middle of winter?
It was official. It wasn't officially winter, but that night it was it freezes at night. You know, Quebec City. It's a northern
That
climate.
is a very cold place.
I have never been that cold in my life. I have lived through -50, -40, but have never felt as cold as that night.
Did
I
you own a
came from
coat?
Senegal with my warmest clothes
Oh,
possible.
yeah, you didn't own a coat. You didn't have winter clothes, did you?
But I had my warmest coat from Senegal.
But it's from Senegal. That's where it gets 50
Exactly.
degrees Fahrenheit, or like what are they, 10 or
Yeah.
12 Celsius?
And I no never had 10. Senegal can never stay 10 degrees
Never
Celsius.
10?
14 is the coldest I've ever heard.
So you had a light sweater. You didn't have a.
Yeah. And I had my shoes was the warmest shoes I had, and
And they were
my
high
my
top tennis
my
shoes.
feet were freezing.
Oh my goodness.
I have never felt as that cold in my life. But I have been through minus 40, minus 50, but never felt that cold.
Oh wow.
It was terrible. And it was maybe I don't remember, but it was freezing, or maybe it was minus one or around
Yeah.
zero. It's hovering around zero. Today, I wouldn't even, I would have like
Yeah.
just
Well,
like a sweater.
you've been there now, what, 20
20
years?
years, yeah,
Yeah.
man, 20 years.
So you're used to it now.
Yeah, I know. Yeah.
Okay, so
So
yeah, so what was your what was the project you got involved in here? What
yeah,
was
so
the
I came in and my supervisor asked me to go around the lab and talk to the postdoc who are in the lab and look at the projects there, come up with what I want or if I have a project that I wanted to work on. And I came across this project on photonic crystals. So it was a postdoc working on it. And so that postdoc unfortunately got recruited by a company and left. So I was left with working on the project by myself. And the first 6 months was very, very hard.
okay.
Yeah, I
And
I am I don't give up.
you're not married at this point.
No, I was
No,
single.
you're by yourself in Canada,
Yes,
freezing your butt off.
and living in the dorm on
Okay.
campus.
And how old were you at this point?
At the time, I was in my mid 20.
25, 26?
Yeah, around that age, mid
Okay.
20, and I was working. You know, I just go to the lab and roll my sleeve and work.
Yeah.
Um, was 6 months was very very hard and wasn't getting me anywhere. But you know, usually when you think that you hit the wall, that's where the lights turns on, and then
Have you ever
voila.
heard the quote, only when it's dark enough can you see the stars?
Yeah, that's what it
Okay.
was.
Would
That
that
was
relate
what it
to
was.
that?
Yeah, I had my eureka moment. It was fantastic. So I was working on making these crystals, and here I arrived in the lab, opened the oven where I used to put this crystal to you know to dry, and I saw this beautiful crystal that has all kind of colors. And I just couldn't stop looking at it. And that was my photonic crystals. I just came up with a way of synthesizing these photonic crystals. It was
So,
beautiful.
I
It
mean,
was fantastic.
so you were building the crystals.
Yes, yes, yes. I was
So
making
I
this
mean
crystal.
that sounds. I mean, you have the knowledge of the optical physics, but you're dealing with a lot of chemistry there too.
Yeah, but in my undergrad, I did a dual degree, one in physics and one in chemistry. That's why.
Okay, okay. I
Yeah,
knew you were. You mentioned you were teaching chemistry, but there's
yeah,
a lot of overlap there.
yeah, yeah.
So
So I
okay,
had a choice actually to go into chemistry or physics, but physics has been always my strongest part. So I
okay.
went to physics. But I wasn't bad actually in chemistry. I actually had a scholarship to study. When I graduated from my undergrad, I had a scholarship to go and do a master's in chemistry, but I prefer to go to physics.
Okay. I would have picked the same. I wasn't as good as at physics, but I have a love for it. So
Yeah, no,
chemistry
physics,
is okay.
yeah, chemistry is good. It helps.
When I can relate the physics into the chemistry, I'm interested. But when I struggle to do that, I just put it aside. I'm not interested anymore. The physics
Yeah,
make
I'm truly a physicist. That definitely is how I think. So
okay.
yeah,
So you get these
so yeah,
beautiful
so it was
crystals.
a complex processes because what I had to do is I would have to make a holographic grating.
I don't even I
Yeah,
know the holographic baseball cards. When you look at it one
yeah.
way,
So a
it's
holographic grating is that um, I would take a 1 inch by 1 inch silica or glass sleeve,
Okay.
slide, and I would make a deposit of a layer of photosensitive resin using
Okay.
spin coating in a clean room. And then I will let it dry. Then I will carry those in a dark, make sure that it's not exposed
No
to
lights
light.
hitting it. Okay.
And then come to my lab, and I had a holographic, an optical setup that allows me to make holographic writing and expose this resin to this holographic light.
Okay.
And then I will go and develop it in the clean room. And when I develop it, what happens is all the exposed region will react to this chemical and will go and will be washed out. And the other material that is not exposed will still remain on the glass or
Okay. So
slide.
then when you rotate it in light, you see something and then you see a different image
No,
depending on.
that is just the first part. That's my
Okay.
substrate.
Okay.
And if you look at the substrate in the on a high resolution microscope like atomic force microscope or so this high resolution microscope, what you see things that looks like an eggshell.
Okay.
So you have like the papers that you can put the eggs in.
Yeah.
Yeah, it looks like an eggshell, and then but the size of the eggshell is 1 micron.
Okay.
It's a regular. It's on a 1 inch by 1 inch. I managed to make this regular eggshell with a pitch of 1 micron, and that's my my substrate. The reason I did this is because when I build my crystal, I use these polystyrene beads, and these
Okay.
polystyrene beads, they are spheres of 1 micron.
Okay.
So I want those beads to come in and settle slowly and settle on those grooves, 1
That you
micron
created.
grooves.
Yeah.
And then it has to be slow enough that it's not because when it's fast, you have a glass, you don't have a crystal. So it has to be slow enough so that the beads can move around. And you
Okay.
have to hit it a little bit, but not too much, so that they can move around. They have enough cinetic energy to move around, wiggle, so that they can grow. You can grow the crystal. It was a long process, but long story short, managed to get this crystal.
Okay.
Yeah.
And then so that's your PhD project.
Yeah, and then you can do the optical characterization, and then after that, one of the things that I did is because between these polystyrene spheres, you have air. So I wanted to replace the air with another material, and that would increase the refractive index. And the nice thing about photonic crystals is that these are unique. It's still a very, the field of photonic crystals research is still very active, and I still
follow it up.
Not that much because I've moved to biomedical optics. So
okay.
After my PhD, so I did my PhD in 3.5 years.
Okay. With the standard, is the standards about 5?
Yeah, 4 to 5 years.
4 to 5. Okay.
Yeah. So, but I was single, living there by myself, very motivated. So, as I used to say to my supervisor, say, I did the work of 5 years.
Yeah.
Literally, but in 3.5 years, because I was
you worked weekends, you did nights.
Yeah, I was just working anytime. I
yeah.
have a mopper. If I'm not doing anything, I just work.
Yeah.
That's basically it. So, and then I got a postdoctoral award to go to work for the National Research Council of Canada as a postdoc.
Okay.
And in Ottawa, and I also had a fantastic supervisor again.
You are getting lucky. I'll give it to you.
Anybody who get to where we are will tell you that they have great supervisors. If not, you will not get there.
Man, if I'm to guess at the percentage of everyone I know who's completed a PhD, it's got to be about half the people who tell me that they had a terrific supervisor, or they had a terrible supervisor, and you're on 2, and you're at 100% right now. So
I have four supervisors. So my master's.
So the other 2 must be terrible.
No, they were fantastic too. Seriously, seriously, yeah, yeah. I was very lucky, very
Oh
lucky.
man. Okay.
Yeah,
So
and
now you're at this government institute. Is it a government institution?
yeah, it's the research arm of the Canadian government.
Okay.
It's called the National Research Council of Canada.
Is
So the
that similar to
campuses,
like, would that be similar to like National Science Foundation in the US?
yeah, like the NIH in this,
NIH. Okay.
but NIH does medical research, but here is engineering, and they do a lot. They do
Okay.
engineering, they do health science, health research, they do a lot.
Okay.
So they even have a campus here in London, actually,
Okay.
next to our university.
You do have a whole lot of research going on in that city.
Yes, yes. It's yeah, we it's a small city, but we really box above our waist. So
That's fantastic.
a lot of
I mean,
research going
I
on.
had a hint of it. I think I'd gone now 3 times,
Okay,
and
yeah,
you get a hint of it,
yeah,
but
no,
I didn't
no.
get to see all of it. But I had a
Yeah, it's a
sneaking
world
suspicion.
class. Yeah, it's a world class research facility that we have here. Like top notch researchers. It's amazing, to see all of that in such a small city. You know,
Yeah.
we are not even 500,000 people,
Yeah,
and
that's not that
really,
small. It's not big.
it's not
You're
big.
not Toronto.
No,
You're not New York,
yeah, yeah,
that's not that small.
yeah. So when I did, so when during my postdoc, so I have spent 2 years there, and I was working on developing optical trapping, and that's what gives me now a hint of biological application.
Hold on. Explain. You said optical trapping.
Yeah,
Explain that to me.
yeah. So there are in optical trapping. What usually people do is that they will have 2 or 4 beams that will come together. It's very challenging, and they will trap uh, something, like it can be an atom, like some molecules or some condensate in 3D. So you can move the whole thing in 3D without touching it.
Oh, hold
So
on. So you hold on. I have to ask.
okay,
If you don't let me get this is gonna bother me. So you are manipulating matter using light.
yeah. So that's the general idea of optical trapping, but we wanted to develop an alternative
Okay.
because we wanted to trap bigger object like large beads or a sperm.
Okay.
And so we wanted to trap sperms
Okay.
for sex.
I'm curious. What would be the advantage to doing that?
Yeah, so to study these single cells and keep them immobiles without harming them, so
Oh.
that you can study them.
Okay.
So so in our application, what we had is we had an optical fiber that was designed to emit a ring of light. Okay,
Okay. Okay.
and yeah, so it was designed so that it will generate when you put it inside the liquid, it will hit so fast that it will generate a bubble, very small micro bubbles.
Okay.
And because now you have now a liquid in the micro bubble, because liquid in the air, like gas in the liquid, will rush to the micro bubble. Now you have an interface between air and liquid inside your medium.
Okay.
And now you use this interface to trap these large particles. So that's how we
And
trap.
so you
Trap.
trap them. At that point, would you be able to move them as well?
Oh yeah, yeah. You move it in 3D, and you can change
How would you move it?
well, you just move your fiber in 3D because
And it
the fiber
drags
is
the
mounted.
bubble? And it drags
Yeah,
the bubble?
yeah, exactly. The bubble is
Oh,
attached to the fiber, and then you can move the bubble, and the sperm is trapped there
oh my
for
God.
more than half an hour. And you can change the air. So I use micro pipettes to gently introduce them into the bubble
Yeah.
so that I can change the air.
So you could put nitrogen in, or you could put,
Exactly. You get it right.
okay.
Perfect. That's what I did. I
Okay.
put nitrogen
Okay.
as a gas inside the micro bubble, and and look at and study the property, the physical properties of this. And it was
That's pretty cool. That's
this is a
pretty
cool,
cool.
that's
Yeah.
cool research. That's very cool.
Okay. And so that so okay, so you started with the crystals. You
Yeah.
moved into trapping molecule or
Cells.
cells into tiny, tiny things and manipulating them. And where'd you go from there?
Yeah, so I spent 2 years there, but I wanted to now really move to medical applications.
Why? What got you going there?
Well, because when I was doing my PhD, it was really during the high-tech bubbles around 2000 when I
Okay.
started my PhD. We were really in high demand.
Okay.
Actually, when I was doing that's why the postdoc who started my project
He
left. Yeah, he went
yeah.
and go to work for Nortel, which was a
Yeah.
huge company here.
Okay.
And now, at that time, company was lining up in our department, in the Department of Physics, because they were coming there, actively recruiting people. Like
Oh
they
wow.
were just telling people, just graduate, we will recruit. You just had to graduate. That's what they wanted.
Yeah.
Graduate. And a lot of people left their PhD, their master, their postdoc, and just go and work for this high-tech company with very, very good salaries. It
Yeah.
was a crazy period.
I can imagine.
Yeah, so by the time I graduated, was the microbubble, the high-tech microbubble bursted, and there was like now thousands, tens of thousands of people with
No
highly
job.
skilled people
Yeah.
looking for jobs, and was a no-go. So I had to reinvent myself again.
Okay, so it was more of necessity almost.
Yes, so I
Okay.
had to reinvent myself. So I asked myself very hard questions and look also where my interests are. I say, okay, well, I'm trained as a physicist, and I know that I can learn anything I want if I roll my sleeves. Then I want to now move to medical applications.
Okay.
So when
That,
I contacted the leader of our group here, the Lawson Imaging, and he put me in contact with my second postdoc supervisor, and
okay.
that's how things started here.
So at this point we've almost made it to where you're at now. You're into the biomedical field. I want to actually ask a couple specific questions.
Okay.
So I mean, it sounds so for me. I think we first started talking because of soccer.
Yes.
So I was an athlete my entire life. I didn't
Yeah.
care at all about school until I actually found research and I got very interested in it. But I was not a good student before that. I was smart enough to get by, but that was about it. But for me,
Yeah,
I'm always
I know
curious.
that. I know you. I know you're smart. I know
I,
that.
I'm definitely I'm curious now. It took me a long time to get there though. So for me, I'm always interested in what brought people to where they're at because I wanted to be a professional soccer player. I probably wasn't good enough to begin with, but then I had knee surgery. I had all these problems, and then I got into bike racing, and I got into this, and I did terribly in school for a very long time. And when I finally figured out that I enjoyed learning and I could separate school from learning, I started doing really well. But it
Mm.
sounds like you already did that early on, because I mean you always say you roll up your sleeves and you learn.
Yeah.
Early on I didn't realize I had to learn. I thought the teacher would teach me, and until I figured out I had to learn, I was really bad at that. So what got, I mean, was there anything in particular that made you want to move into physics? Basically, is there, I mean, you got your undergrad in physics and chemistry. Through school it sounds like you were already kind of heading that way. Where, I mean, was it your parents? Where did you see a movie? Did you what was it that
No, no, literally, because my parents were not highly educated. My dad was an electrician,
okay.
so I learned the
Which
hard work really, really
yeah.
from him.
And there's some science to that.
Oh
It's
yeah, no, no doubt about it. He was not highly educated, but extremely smart.
okay.
Maybe one of the smartest people I have ever met in my life. Extremely smart.
And hardworking.
Yeah, and hardworking. So
Okay.
he did well of himself. So for guidance in school, I didn't have like parents helping me choose whatever I want and so on. So, but you develop maturity very quickly when you live in third world country
I,
because
would you say I can imagine that. But would you say that part of it might have been just seeing your dad working?
Yeah, maybe it's a part of it. I'm sure he was definitely and still my role model in many things. When things gets hard, I say, well, you know, if you work hard at it, it will get done,
Okay.
and that is the truth. You, it doesn't matter how hard it is, how complex it is. If you use your brain and you work hard and you're very strategic, you will get to the bottom of it.
Okay. And then on a totally unrelated note, was your dad any good at soccer?
No, my dad
No?
passed away actually. Yeah, actually 10 years ago now.
He
So
did? Your
yeah,
dad
he
did?
passed away.
Oh, I'm
Yeah, he
sorry to hear
was.
that.
No, it's fine. It was there's like now almost 11, almost yeah, almost 11 years now. So
But he didn't play soccer with you?
no, he didn't play soccer with me.
Where
So
where'd you where is it just with your friends?
well, I play soccer with my friends, and literally, when I become older, that's when I really play soccer the most. Because when I
Okay.
was younger, I didn't have a lot of time to do. So I had my schedule very busy because my
Yeah.
dad, I would go to school almost all the time, and if I wanted to go to school, I would go because he was an electrician and he had employees who would go and work in construction. I would go during the work with those guys in the summertime, or I will, and he also had a hardware store, and or either I would go to the hardware store. So I was busy. He kept me
Okay.
busy.
Okay. That's what I
Yeah.
mean, I got you there.
Yes.
Okay.
So when I become older, then I had the chance to play soccer, and I discovered that I was actually pretty good at it.
That's a good thing to find out. And
Yeah.
you're still, I mean, the season must be picking up. The weather's nice.
Yeah, I'm running right now. I run 3 times a week.
Okay, and
So I run on
your
Monday,
back's
Wednesday, and Friday. So today, this morning, I went for a run. So I go early, then I don't
okay.
see anybody because I wake up at between 4 and 5, depending on the day. So
Even so, is that even with the shutdown? I'm assuming y'all are shut down too.
yes, yes, yes. Well, we are
So
because of the
in your
pandemic. We are
schedule,
shut
you're
down.
still getting up that early, even though,
Yep, yep.
oh man, my normal waking hours are usually 5 a.m. and it's moved up to about 7:30 now, and
No,
it's
I
gotten
don't.
harder to get up at seven than it was at 5.
No, I wake up. My alarm goes off. The latest that my alarm goes off is 5.
Okay,
So and then I'll wake up, I'll get ready, and then I will go for my run. Usually when I come back here, it's around 6 a.m. I'm
okay,
back, I shower, then do my other stuff, and then I'll get my coffee and start working.
very good. Okay,
No,
so
it's good.
so
So
in relation to how you got there, which it sounds like it just, I mean, you found a topic you liked, you studied hard, and you had a desire to do that.
yeah.
I mean, for seemingly went that route. Um, when as you're going there, you're now a physicist, and there's such thing as physics envy. I don't know if you've heard of that. It's a play on an something I won't say, but it's with scientists. Every scientist wants to be a physicist. Have you ever heard that?
No, I've
Okay,
never heard about that.
it's called physics envy, and it's a play on a dirty term. But
Okay.
um, but you're essentially a scientist in a field that most people see as incredibly difficult. I mean, it's so much math and it's so much interesting comprehension and view of the world that a lot of people struggle to deal with it. What has been the hardest thing for you to learn? Like
Quite
you're in,
frankly, people will say, they just talk. But quite frankly, because I didn't do physics in my lower year of high school. I really wanted, but
okay,
our principal had a lot of power in our school, and he would decide who would go to is it- to the physics class, and he wanted to have the best students in a class that was studying Arabic, and I don't understood that. So I wanted to do physics from like fourth after after 2 years of high school, but he wouldn't allow us. So I lost those 2 years, and when I started doing physics after my fourth year of high school, uh, so I was in a class where people were have already done 2 years of physics.
yeah,
And but I catch up very quickly. I can tell you that the language of physics is something that my brain just understands.
Okay.
Just how it is. Seriously, that's how it is. I just understand it.
Okay. I mean, but like, as we're going through it, I mean, you're dealing with optics, which I still struggle with. Like just basic lenses. Like I'll look at them and I have to sit down and focus to get through it. And then, I mean, you have to deal with statistics. You're having to deal. I assume you have signal processing because you're dealing with detectors and sensors. Um, you're dealing with
Yeah,
what else?
differential equation, light
You
transfer in
have
tissue.
computer programming. You have the calculus. You have the linear algebra. I
Yep.
mean, what somewhere along the way there had to be something that you had to sit a few extra minutes to get through. What?
Oh well, I can tell you, I work hard at these things. It's
Okay.
not, yeah, I understand them, but be, because I think it's because I sit down and just work at these things, because I love them, I may actually work more than most people would do, but because I like them so much that I don't feel it like work.
Yeah.
Oh yeah, no, these are not things that come to you as a revelation. So you work hard on that.
Okay.
Oh
But
yeah. These things are not things that you just look at them and you understand. And yeah, you sit there and you work hard at them and you understand them.
so
That's how
on
I do it.
okay, on the other side of that,
Hmm.
do you see any students or any like new colleagues that are coming in that struggle with any particular thing?
Well, because I teach, because I'm a university professor, so I teach. I have class. So in my teaching, I try to decouple the math and the concept, physics concept.
Okay.
And it is still a moving target, but that's my goal, so that the people who struggle with the math will understand the concept and see the potential application. So they want to be scared, and I try to tell them that you don't need to actually uh, be able to do the derivation of the differential equation and this thing. You can just use a solution that are
Yeah.
accepted and use computer programming to program and get results. And I use MATLAB to do this demonstration in class. The way I show them the equation, it looks very scary, and show them the solution that looks very scary as well. But I say, okay, well, this is a MATLAB program, very simple, a few lines of code that allows you to program the solution, and then you can change this parameter and see the results. So you can have
Yeah.
a feel of what it is. But there are students who like the math, who come in and work on the math, and then you try to touch very wide range of people's interests and comfort level. So
Then what part of the math is the hardest aspect? Is it
I think it's calculus.
the calculus? Okay.
Yeah, I think that's the part. We do a lot of metrics. Knowing metrics algebra also helps a lot in our case, because instead of when you do programming, instead of you writing an F loop, you can just do matrix multiplication, and that instead of having an F
Dot
loop,
star.
yeah, you just do a dot. Yeah, you just do a dot product, and then you now multiplying like large matrices very, very quickly, and that makes your program much more efficient.
I think I'm one of the students that math is definitely not. I was good at the low levels of math, and then I struggled very much in the higher levels. But when I
Well,
see it, if I
most of the
see it,
time, I think it's teachers. Quite
okay,
frankly, I believe that as a human being, we are logical creatures, and if things are taught very well, we will grasp it, we'll understand it. Quite frankly, that's why I put the onus on myself when I teach. So if I lose any student, it's not the student's fault, it's mine.
okay.
Yeah, you really
I
have
always
to.
tell my girls that if I'm telling them and they don't understand it, I'm not explaining it well.
Yes, that's true.
It's not that they're dumb. It's not that they're it's because I need to reword it in a different way.
Yeah, you're right.
Um,
That's my belief.
but
I'm a strong believer in that.
one thing that I did, and you mentioned it, one thing that I found extremely useful is I can understand a computer program much better than I can understand, you know, all the mathematical symbols on a page. If
Exactly.
you know
So
it's the same thing, and I
And
get
you
it.
don't, because if you can program it, if you can take the equation and program it and change the parameter, get a good feel of it, that's all you need,
Yeah,
literally.
and it makes I can comprehend what's happening
Yes,
when
and
it
that is
with
what is important.
yeah.
That's what is important. You don't have to be a math wizard. What you need to do is to have a good feel, and that's all about physics. Because in physics, for instance, the equation that we use the most to describe light propagation in tissue is called the diffusion equation.
Okay.
It's an approximation to the radiative transfer equation. These are equations that don't have general solutions in general. We make approximations.
Yeah.
And quite frankly, yeah, you get these solutions that are approximations. So you have to, as a physicist, you have to know where, what all these, um,
Kind of
approximation that you made, and
what is the
compare the solution.
confidence interval and stuff like that?
Exactly,
Yeah. Okay.
exactly, exactly,
And I
exactly.
mean, this goes back to your first statement of these beams of light that you're shining in are basically clouds, right? So
Yes.
your cloud has to have a lot of wiggle room
Yep.
as to what that shape or where it's going and how it
Exactly.
propagates.
Exactly.
Okay.
Exactly.
Okay. Let's see. I have a few more, and then I just want to chat with you. And I know you're getting late over there, so I don't want to keep you too long.
Okay.
Okay. So this is for my own personal enjoyment.
Okay.
What in your field has got you really excited? Is there any new
Whew.
developments or anything that's come across your table that you've seen that you like gets you kind of giddy?
Yeah, I think the new concept that we are using for our hand imaging is called compressive sensing.
Okay.
That has
Why
a
is it
huge.
called compressive sensing?
So compressive sensing is, it's called compressive sensing because we realize that if you look at an image, for instance, if I take the image of yours or mine right now, and we analyze it, we know that this image can be reconstructed with much fewer pixels than the number of pixels that our camera is displaying.
Okay. Is that, I mean,
And
so you have like a JPEG, which would be a compressed 2D image.
Uh, no, yeah. So compressed sensing go beyond that because that's the digital compressing. So here
Okay.
you do the compression during the data acquisition because in JPEG they acquire the high uh, like resolution data and then they compress it digitally. But
Okay.
here you do the compression during the acquisition.
How? How does that
So
work?
because like you have an image that is sparse, the sparsity comes from the fact that I can represent this image with uh, uh, very small, a smaller number of bases.
Acquisitions or
Yes. So
okay,
let's say
so
that if I take your image and I have a checker board,
okay.
a checker on the overlay on your image. I
Okay.
can and I randomly a checker will be black and white, and I can randomly uh, change those checker the speckle of the checker, and then if I have enough of those to have a base. For instance, if your image is, let's say, 1020 by 1020, which is a large number of pixels, I can, instead of acquiring that, I can acquire that using maybe, I can do a 90% compression and still have
Okay.
a very good image.
So
And now
if
you can see, instead of using like a camera that has a large number of pixels, I can use a single pixel camera that can acquire very fast and do this, acquire this images.
so this would be if I were to relate it to a time series, it would just be like decreasing your frequency, your
Yeah,
acquisition
without
frequency.
losing, exactly, without
So
losing
you
information.
still like you have a sine wave coming in, you can do a couple values per wave, and you still have your signal, and you can reconstruct it that way.
Yeah,
But you take far,
without losing information. You
yeah.
have a
Okay,
sine wave. Say, let's say that you have a complex wave where you
okay,
have many sines,
okay,
but you know all the signs that are there,
okay. So
and
you have
then
a
you
Fourier. It's a Fourier transform.
exactly.
Yeah.
It's
Okay.
similar to the Fourier transform.
Okay.
Yeah, it's similar to the Fourier transform,
Okay.
definitely,
So you're
because
dealing.
you only have to measure the coefficients, and that's it.
So what has you excited about this? I took you down a
Yeah,
rabbit hole.
no, the application are huge. For instance, you can now start to do 2D imaging in region of the spectrum where there is no 2D camera. First, and you can have a 2D, you can build now a camera that is in, we build a time resolved camera using a single pixel, like those single detectors. So now you have a 2D camera, time resolved camera using just a single pixel, one PMT.
Okay, I'm blown. Okay.
It's fantastic. It's really like,
yeah.
It opens up a huge potential. For instance, now we know that we have, there are some region of the infrared where we don't have 2D camera like CCD or CMOS. But now by using this, but we have single detectors like photo detectors that are single pixel. And now we can use this technology to develop camera in those 2D camera in those regions.
Okay.
Applications are huge. You know, yeah, it's
okay.
A very exciting field.
So on the side of wavelengths, so you mentioned we're diving into, you have some infrared stuff.
Yeah.
I mentioned I'm not very good in optics, but I love it. Everything about it. And the thing that blows me away is the fact that you have all these waves traveling around at all times that you can't see, and they don't seem to interact with each other.
No.
Like you can have two waves crossing each other and directly across from each other. You know, someone over here sees something over here and I see something over there, and there's no interference. That blows me away. It's amazing to me. And I'm curious, from someone who understands it a little bit more in a bit more detail, you know, you have so much invisible world around you, and the only thing that gives you an understanding of what you see is when your eyes convert a strange wave into a picture that your brain decides what it looks like. So my question is, this is a big one. My question is, if I can't reliably tell you what something looks like because it's inherently on my brain side, what exists out here? Does that question make sense to you? Because what I see is light bouncing off of matter, and I don't know what that matter is, but it's there. The light bounces off, my eye reads it, it converts it to an electrical signal. My brain says that looks like a cat.
Yeah.
But that's because of this interconnection between my eyeball and the brain. That doesn't mean the cat looks like that.
Yeah.
So from your standpoint, you know, how often do you go down these thought process and think about?
That's a very philosophical question, and it is, you know, this may be a
do you avoid those thoughts just to keep?
No, I love those.
Okay.
Actually, if I wasn't a physicist, I think I would be a philosopher.
Okay.
I believe that we are, well, this is just esoteric now speaking, but I believe that, you know, because I see the world as a physicist.
Yeah, which is a unique view.
Many dimensions.
Yeah.
So to me, the fact that, you know, I see the world in 3D doesn't mean that the world is really 3D.
Yeah, I've always been curious. Yes. Yeah.
Yeah, I think the world is not just 3D.
Yeah.
It's just because that's what we can do. That's how we can. I believe that maybe someone, or if we had the technology to have now another axis which is different than our linear time, so we can say that we have now a 4-dimension with time.
Yeah.
So if somebody, or if you had the possibility to have now a 5th dimension where you can stand and see the world in 3D and time, then you can see before and after and during.
So almost, I mean, yeah, I mean, this is in a 3-dimensional mindset, because I can't escape that. But you're essentially up on a cloud looking down, and you have strings of time that you can view. Okay.
Yeah, so you have a 5th dimension that will allow you to see our world over time.
It would separate you out of the time.
Exactly.
The 5th dimension is separate. It just is like the removal of time.
Yes.
Okay.
I think about that, and that would be like like so awesome that you can see before and after, see now.
I've always
Mhm.
enjoyed the thought, like if I wake up one day and I'm just I had a bad dream or something, and I think about something that I was doing 10 years ago that I love doing that I can't
Yeah,
do anymore, and it makes
yeah,
you feel bad. I
yeah.
always go to the thought of, well, past John exists and he's enjoying that right now, so let him enjoy
Yes.
that. Because I've always kind of thought that, like, my kind of idea behind it was that the Earth is only so it even if you were to go back in time, you would
Yeah.
have to go back to that space in time. And
Yes.
unless you can do that, you would find yourself not on Earth at that location, right? Earth would be somewhere over here and you would
And
be
you'll be
back in
completely
time.
different,
So
probably, because
so I
your
would
constituents.
yeah,
So we are made of what we eat.
yeah.
So some part of your body wouldn't exist because that food that makes that part of the body didn't exist at the time.
Oh yeah.
Yeah, all kind of things.
I
You
haven't
may
thought of
have
that.
balls.
I haven't thought of that. No, I always just pictured, so if you separate out the time, there's always different versions of you living at that moment. So I always
Yeah.
kind of like to kind of come to that and say, it's sad that I don't get to do that, but past John gets to do that. So that's fine. So
Yeah,
I
so
don't know
it's
if I believe it, but it's nice to think about.
you can imagine, like, it would be fantastic if somebody could now have that fifth dimension, and maybe if we have that, then we could travel in time and explore new planets
Yeah.
and explore new spaces, because the likelihood is that the universe is so big that I just read, like, this week or last week, that they discover a new planet that is roughly the size of Earth. Well, they think they discovered it,
Yeah.
and it could well be a planet that is situated in the sweet zone around a star, and they may be live there. I would say, wow, but
Yeah.
it's about 300, no, 3,000 light years from us.
So that would take 3,000 million years.
No, more than that.
Oh, at
3,000
the speed
light.
of light. At the speed of light.
Yeah,
Okay.
as the speed of light to go there will take 3,000 years.
Oh my God. Okay. Yay.
Well, or maybe more than that. I think I
Yeah.
remember the 3,000, so it was something unrealistic. And
Yeah.
then I come back to my thought and say, well, if you could have that fifth dimension where time is no longer a limitation, then you
So
can go there
so
and see that.
your idea is that NASA and other space agencies need to stop worrying about rockets, and we need to start worrying about dimensions. We
Yes.
like don't worry about getting there. Let's worry about the time aspect.
Yeah.
Okay.
That's our main limitation, because we are in this
Yeah.
3D physical body that is subjected to time.
Okay.
How do we get out of that?
Okay. And you mentioned how busy you are. Do you ever watch sci-fi movies or read sci-fi books?
Well, I
Or do you watch Netflix? Let me just
I watch Netflix sometime when my wife and kids have found like a movie that they want me to watch. They will
Okay.
grab me in the basement, because I have a home theater in my basement. It's very nice, actually.
Okay.
I have a real home theater, and like big
Like
screen
reclining
with a
chairs, big
projector.
screen.
Yes, big screen with a projector. It's very nice, but you know,
I know you're
there,
busy.
there is a
What?
saying in my native language, Wolof, that says that when it's easy to pick up things on the ground, like to pick up diamonds on the ground, it becomes hard to bend.
I like that.
Yeah,
But so
yeah,
if I mean
if I had the time, man, to watch TV, and I have so many
you're gonna be
channels.
too old.
I have so many channels, so I have all kind of channels in my
But if you could watch anything, what kind of shows do you like? Because I
documentaries.
yeah, okay. I am a huge fan. I've discovered of my favorite show that I've seen in the last 5 years was Peaky Blinders. I don't
Peaky
know if
Blinders. I'm gonna write it down, and I will try
it.
to
So just a warning,
uh-huh.
it's about gangsters in like 19 teen like pre World War One or post World War One era,
Okay.
and it's very gory. There's a lot of inappropriate adult stuff going on,
Well,
but
I will watch it by myself.
it's it it I want I I got really into it. I'll say that much. And you have to watch at least 3 episodes before you make an opinion, because the first
Three
one or
episode, okay,
two are okay, and then after the third one, you're into it.
okay. And
But
it's on Netflix.
it's on Netflix, and it's very gory, and it's rough, but it's
But I don't
really
know if I don't
good.
know if because I know that Netflix in the States is different from Netflix in Canada, but I will have a look.
I think I learned that when I went to Canada because I tried to watch something in a hotel room and it wouldn't let me.
No,
I had to
yeah,
have a
yeah,
Canadian account and I didn't have one.
yeah. I know it's different. It's different, but I will check it and see if I can watch it. I can watch it on my laptop on my phone and let the kid use the TV like this home cinema in the basement. So
Okay, so I got one last question for you, and then we can hang out and chat if you want.
yeah.
Um, if you had to start over, you're back at like age 10, and you had to go in a new path, would you have followed the same path you went in? Would you have got? I always ask, would you go into finance? Would you become a medical doctor? Would you become a policeman? Or would you become a teacher because
Well,
you were on your way to be a teacher? Like, well, I mean, I say teacher, like a high school teacher rather than a professor.
well, I love teaching, and I think I would prefer. I'm actually very happy with where I am. Sometime when I'm very hard on myself, I just try to remind myself where I came from. I came from a third world country, from a not rich family, and got where I am with on my own. I never had any loan. I always have scholarship and to pay for all my schools. My parents didn't pay for my post-secondary education at all. So they put me in private school when I was in primary school. That was through their glory. But yeah, so I got there where I am. So I'm pretty happy with what I achieved.
Yeah.
So I would have want to have achieved more, and I hope I will have be healthy
What
and live long enough to be able to achieve all my goals.
what would
Especially also coming back and training highly qualified people in Africa. That's something that is very close to my heart.
okay. So on the time when you get your feet on the ground, the kid you have one child, right?
I have two,
Two. Okay. And how old are they now?
14, almost 14 and 10.
Okay. So when they're out of the house,
Yeah.
you would head back to Africa and do teaching there? Like maybe
I
maybe
wouldn't
not all
wait
year.
until then. I'm not waiting until then.
Okay.
I'm already working on this, trying to get to have funding in place so that I can bring in here young university professor from Africa, and then they can spend 6 months in my lab training and go back to their country so that after 3 years they will be trained, well trained, and we will build a network across Africa of these highly trained people so they can interact together and they can and we'll try to put in place funding that they can start labs and do and apply this technology because optics is really
Yeah.
ideal for developing country. It's the state of the art. There are a lot of things that you can do with optics in the medical, in biomedical application that you cannot even do with the state of the art medical imaging, MRI, and
Oh
others.
yeah.
Mobile is cheaper. So yeah, I really want to do that. And on top of that, yeah, the teaching, I can do teaching remotely. I go back to Africa quite often because my mom still lives there.
Okay.
And still have a lot of friends who still live in Africa. So they are close friends that I keep in contact with them through, because I'm not on social media, but
Yeah.
with Skype.
I've
Sorry,
I've officially I've officially removed everything of mine but LinkedIn. I still have a LinkedIn
yeah, I
account,
have a LinkedIn and I
but all the
use,
other ones I found myself wasting too much time, or I was getting
exactly,
mad,
it's a waste
or
of
I'd get
time.
mad for no reason.
No,
And
I will have a Twitter account for my lab because we are finalizing the building of the website of my lab. But yeah, other than that,
okay.
I'm not interested in those social media. It's just a waste of the time most of the time.
Well, if there's any way that you think I could help with your project over there, I would love to throw a hand in.
Perfect. I will
So
keep
if
that in mind because
please, yeah, keep me on your mind if something comes up and you think I'd be a good fit. Let me know.
Oh yeah, absolutely. I think yeah, I will definitely keep
I
in mind because this is a huge project. I cannot do it by myself. I will need a lot of help from a lot of people. But I believe that in our community, in the FNIRS community, I may find allies there who will be willing to
oh, I'm sure.
embark into this and help us achieve this because it will be also our benefit because we have this huge pool of talent sitting there doing and
Yeah.
not being tapped at all.
Well, and I mean, you showed me some of the imaging aspects. You guys have some good toys there. You
Mhm.
really have a really good facility there.
And we build every single thing.
That's fantastic.
And now you see we build everything.
Yeah, that's fantastic. And that's got to
Yeah,
be fun.
it's fun.
That's
It's
got to be
definitely fun.
fun.
And one aspect of the thing that we didn't talk about is the algorithm development. I do a lot of
Yes.
algorithm development.
How are you on time?
Uh,
Maybe
yeah, I,
15 minutes?
yeah, 15 more minutes.
Let's
We
talk
should
about
be.
algorithm development. And well,
Yeah,
let's see
so
what
we
time is
develop
it?
a lot of algorithm.
Okay. You're at 9 o'clock now. Let's go to 9. Is 9:20 okay?
Yeah,
Okay.
yeah. So we do a lot of algorithm development, and this is to analyze our the measurement. So the measurement we acquire with our devices, because how it is in optics. You have a signal, and you have to do signal processing.
Hmm.
And this signal processing include light modeling, some other signal processing like wavelet or other signal like Fourier
Yeah.
transform, sometimes statistics and all those things. So right now, my lab works a lot with using uh, continuous wave nears
Okay.
also,
That's the one I'm
but
familiar with.
hyperspectral.
So multiple, like every spectrum.
Yes,
Okay.
one wavelength sample the sampling the sampling of the wavelength will be one wavelength. For every wavelength, we will acquire every wavelength between 600 nanometer and 1,000 nanometer.
Is that by 1 nanometer increment?
Yes, but
Oh,
we
wow.
acquire all of them simultaneously using
Okay.
a spectrometer.
Okay. So
And
that the analysis on that is heavy.
it's interesting because we
Okay.
have advanced technologies and advanced data analysis processing. So we right now we work a lot on that, and the application is on brain monitoring.
Okay.
So we have devices that are used in the clinic. So we monitor neonatal brain in the intensive care unit. These are preterm babies.
What does that extra, what do all the bandwidths give you? Different molecules?
Yeah, exactly. Because if you
Okay.
have many wavelengths, so you can now monitor important molecules in tissue, which
So
are
there's
toxic.
hemoglobins,
Yeah, water.
cytochrome,
Exactly.
oxidase,
Water.
and water.
Yeah, cytochrome. You know that cytochrome is a very sensitive biomarker of oxidative metabolism,
Okay.
and so we use that. Our aim is to really quantify. So we can quantify cytochrome in the neonatal head. So that's something that we are currently doing.
Okay. And for that,
Mhm.
I know there's been from my discussion with a few people, it
Mhm.
seems to be a lot of discussion of how many wavelengths do you need for that?
So
And
we
I've seen as low as 4, which I don't know if that's true, and I've
stop.
seen up to about 8 to 12 being pretty ideal, and then some groups are saying you need this hyperspectral measurement.
Yeah, we took the road of the hyperspectral mirrors
Do you think that's needed specifically for cytochrome?
because for us we do derivative spectroscopy so that we can very confidently measure the other chromophore, which is hemoglobin, oxygenated and deoxygenated hemoglobin, and water.
Okay.
So we can measure them very confidently at baseline, and then we use the changes in the signal so that we're not dealing with a lot of uh, crosstalk.
Okay.
So that we can isolate the cytochrome signal very well. I strongly believe that the hyperspectral is needed in order to reliably measure cytochrome.
Okay.
But I may be it's because that's a route for us. It's the safest route. That's a route we take.
Okay.
Yeah,
That
so
makes
there is a
sense.
lot of algorithm development in that regard. So
And
I have here right now 3 students working on that.
and how do you like that aspect of it? Because it sounds like a lot of the stuff you did, you were building, and now
Yeah,
with
no,
the
but
algorithm stuff, it's a, I mean, you're still building, but it's a very different type of building. Do you prefer that or prefer the?
what I love all because you know the algorithm need the device needs the algorithm,
Okay,
and it's a complementary. If you want to have something useful, something that you can use, you cannot just work on one aspect. You have to work on both aspects. So we have this clinical application where we monitor neonates in the intensive care units, preterm babies on babies who have hydrocephalus, which is a feeling of liquid in the ventricles. So
yeah.
we monitor them. We also have a clinical application where we monitor adult patient going through cardiac surgery.
Is for the hydrocephalus in particular, is optical spectroscopy the ideal for that, or is there like is ultrasound or Doppler or something
Well,
another?
ultrasound can give you the image of the ventricle, but it doesn't give you the functional information.
Okay,
So we want to see is the tissue, because hydrocephalus, the brain will swell and will squeeze the tissue, and you want to know if the tissue becomes ischemic or not, because that's what we're going to start to have
okay,
detrimental effects on the brain.
okay.
So that's the way the optics comes in.
And
So
on you go ahead, keep going.
yeah, I was saying that for the adult subject where we do monitoring during cardiac surgery, because when you have cardiac surgery, the organ that you worry the most are the brain and the kidney, because these are organs that are very susceptible to ischemia. And during cardiac surgery, most often you have a lot of derangement for the perfusion. The perfusion is altered because the heart is not pumping. You have using a machine that do the perfusion, and there are a lot of issues with that. So we monitor the brain to detect ischemia. Right now, we are conducting a pilot study to see how can we compare, how can we reliably measure these parameters, flow, metabolism. We use also DCS, which is a technique, an optical technique that measure perfusion in tissue, and combine
I've
it
come
with,
across DCS a bit.
yes.
Yeah.
You know, it's a lot of technology. We do a
Oh
lot of
yeah.
technology, and each of them has specific applications, and yeah.
And so
That's
that
maybe that's why I'm busy.
no, absolutely. But no, that's fantastic. And I get why you. I mean, you say you work all the time, but it doesn't feel like work. I get it. I mean, everything you tell me just sounds so cool.
It's
And
cool. It's
just
really
and I
cool.
mean, it's not just to me. It's not just the application, but even the imagination behind it. I mean,
Yeah,
it takes you know knowing and understanding what's actually happening in order to actually work with it is such a cool aspect. And yeah, I mean, the physics side of it, we went down that rabbit hole, but I mean, I see why it's so exciting when you get it to work and you know why it works.
yeah.
It's not just happening, you know why it's happening. I think that's such
Yeah, I know it's fantastic, and
yeah,
we had a project that was completed where we use our people. So colleague, a graduate student here in our one of our researcher. He's an intensivist. He's an intensive care doc, and he will use it to monitor sepsis patient and intensive care patient. And we had another guy who's a perfusionist, who's a graduate student in our department, in our program as well. He's supervised by one of my colleagues, and he used one of his device to monitor the muscle of patient going under cardiac surgery. And we analyzed the data already. And I
what
have
what
also a
muscle
project.
what muscle is he looking at? The cardiac muscle?
We're putting it on a thigh muscle, because if you have a systemic derangement in perfusion, the question we had is it, if we monitor the muscle, is it enough to pick up, uh, uh, perfusion derangement in this patient?
Okay, because if it is, that's a fantastic tool.
Yeah, exactly,
Yeah,
because the brain is very complicated, because you have to
yeah,
go through the skull before you get to the brain,
yeah.
so
The
it's very
muscles.
challenging. Yeah.
Yeah. Okay.
And we also, now I have another project with my colleague who is a supervisor of that of those guys that I just mentioned, And we are now going back to the bench where we use animal model of sepsis and where we want to monitor the brain and the muscle simultaneously using hyperspectral mirrors and DCS to monitor both perfusion and metabolism and see if there any correlation. And we will compare this to intravital microscopy where we can see the microvasculature clearly and do the correlation. It's a lot going on and very interesting work. It's
That's
really
very
exciting.
interesting work.
Yeah, it's very exciting.
Okay, and how does the family put up with all these work hours? Do they ever give you
I try
attitude
to
about
find
it?
time to, right now, the weekend, now lately, I try not to work on my university research stuff on the weekend. I spend time with the family, try to work in our property together, so spend time together and talk. And the pandemic has helped in a way that now after 7, I stop completely, and then I can spend time with the family, and we talk, we do stuff, and even during the day, I can see them, I can go
Yeah,
and tease them, talk to them. So
have
we spend
lunch
time.
together. Or,
Yes,
yeah,
yes.
that's that. I've been having a similar. I change a lot more diapers during work hours than I used to. So
Yeah,
it's I
yeah.
don't
You
know.
have a little one. You
I
have a
don't know.
little
Yeah, I don't
one.
know. It's been a while since I have an 11th month old actually.
Yeah.
So yeah, we have a little female baby version of me. Her face looks just like me, but longer hair, and she's half Puerto
That's,
Rican, so
that is cool.
yeah, she
That,
tans better than I do. But
that is definitely very cool.
yeah, so yeah, it's been interesting.
So how is the whole family doing?
The family's great. The older girls, we have a 7-year-old, a 5-year-old, and then the baby.
Yeah.
The 7-year-old did really well in school. She's really been in. We did our first science experiment actually.
Cool.
She wanted to know. The initial experiment was, can me and my sister run in the hallway, and then I'll practice a bunch, and if I get faster, then the experiment worked. So I said, well, let's do it, but let's change the experiment a little bit. So basically, she would run in the hallway. We timed her, then she'd do 3 little runs.
Okay.
And then over the next 10 days, we did 3 runs every day at lunchtime, and we'd time them. And so we did a spreadsheet, and we'd record the
Fantastic.
times. And we even did a t-test from the starting times to the ending times, and to see if there was a significant difference. And we got a p-value of 0.023.
Oh,
So
wow.
we improved by 0.93 seconds.
Oh, fantastic.
So we
That
did
is a real science experiment.
we did our first real science experiment. So that was
That is
fun.
fantastic.
And then the 5-year-old wants to watch Netflix and eat ice cream. She has no interest in any science. She has no interest in any of that. But she's starting to get interested in
Well, it will
reading.
come. I think
Huh?
that could come because it
Yeah.
depends on the environment. So if
Well, that
we are
was
in an environment science is talked about,
yeah.
like science,
And that was me. I just wanted to play soccer all day. I didn't want to go to school. I didn't want to learn anything. And now I spend the whole day. I finish work, I pick up a book, and I read about. Right now I'm reading an MRI book. I'm reading
Really?
oh yeah. I've just finished a CT book. And now a friend of mine, a very good friend who I hope to interview on this, he actually is the author of a cochlear implant book. He is an audiologist, and so he sent me his textbook as a gift, and so I
Fantastic.
just opened it yesterday. So I haven't even gotten to the first chapter because I've read like the prologue and and I'm starting the first chapter tonight. So
That is interesting. So
so now,
you're going to be much more educated than me in science.
I highly doubt that, but I'm hoping I
Ah,
can. Well, I like learning it. I realize there's a quote from Albert Einstein, and I think I believe it. But he said that science is a terrific hobby, but a terrible job. I don't know how you feel about that.
well,
But for me,
a hobby, I agree with that because today, if I was a millionaire or billionaire, I would be
You
doing
still,
research.
I believe it.
I
And
would be doing research.
that's for me. I wasn't. I'm not very gifted at it, and
Uh, if
and
you, I think if you put your heads in
well,
it,
I will get it. I will get the answer, but it will take a lot of time, and it will take a lot of frustration, and you know, I finally get there,
that's
and
like me. That's like
well,
me.
what I realized was, you know, I if I take on a different career that
Mhm.
was less stressful and gave me enough time, I could do this on the side.
Okay.
And then, you know, towards the end of my career, I could become an instructor. And I think I like the instruction part. I like trying to learn it well enough so I can explain it to my kids, you
Excellent.
know, and I get to tinker. But if I had to do it as a job, I think I would be too stressed.
It is stressful sometimes, most of the time, because we have deadlines, and you have
Well, it's not easy
requests from all
problems.
the time. You have requests from all the time, and you have pressure from the institutions, pressure coming from all over the place. So yeah, that's the part that is the toughest one. But
Well,
it's exciting.
this is how I looked at it. Well, I don't. So another quote for you is Stephen Hawking said the only two types of people on Earth who do what they love is scientists and prostitutes. That was a Stephen Hawking quote, and
Oh man.
very inappropriate. I understand it. I get it. Um, but what I think is the most stressful thing for me is what you're doing by definition no one has ever done.
Well, you have to do things that nobody has ever done.
And
At
what
least,
which means that what you're working on is incredibly difficult. And when you're dealing when you throw in a deadline and you're trying to work on a problem that is so many levels and so much going on, it's so it's so stressful. But for like the way I saw it is, okay, well, what if I don't have to do things that no one has ever done, as long as I haven't done it.
yeah.
You know, if I'm learning something new, I get at least some level of exhilaration because I figured
No,
it out.
absolutely, it is. It is.
You
It is.
know,
It is.
and the stress level has decreased drastically.
Yeah,
So
because
that
for us, you have to publish in the best journals, and
yeah,
to publish in the best journal, you have to do things that nobody has ever done, and yeah, and you try to stay ahead of the game. You need to have inspiration. You have to, it is what it is, but it is a very exciting job. It doesn't feel like a job sometimes. Sometimes it's very stressful because what it is, that's what it is. You have pressure from coming from all kind of places, and you have a lot of requests that you have to shift through to see, well, do I answer this request, do I help here,
yeah.
because you have to also prioritize your work. It is
Well, and
interesting.
you know, and I tell you, you know, what I just said. You know, I tell you that you know the stress level is so high and the problems are so hard, and you know all that. But all that said, my dream job is to become a medical physicist.
Oh well,
I mean,
man, that's
you know,
fantastic.
so I mean, if even with all that said, I still want to do
Yeah,
it.
yeah, it is exciting. It is
So
exciting.
you know, I love what you do, Mamadou, and I you know I think we've reached time.
Yeah, yeah.
Um,
Thanks for talking.